DSP. DSP stands for Digital Signal Processing, which deals with the processing of digital signals to get desired output or responses using digital system processors. The basic processes or operations that are done on digital signals are filtering, scaling, integration or differentiation, addition or subtraction of two or more signals, and modulation. But why? Why DSP? Why not analog signal processing? Why should we convert analog signal into digital signal and then process it? Well, the answer lies in its properties, the properties of digital signals. Flexibility. In DSP, for different operations, you only require to change the software program. But for analog systems, a new design of hardware is required. Accuracy. For accuracy, you simply need to change the sampling frequency and the AD converter. Storage. Since digital signals are finite, therefore they can be easily stored, can be easily accessed, and can be easily read again and again. Now, let us see the applications of DSP. The applications of DSP are as follows: audio signal processing, audio compression, image processing, image manipulation, video compression, speech processing, digital communications, digital synthesizers, speech recognition, mobile phones, weather forecasting, seismology, seismic data processing, analysis and control of industrial processes, biomedicine, medical imaging such as CT scans, MRI and X-ray, nuclear spectroscopy, radar, sonar and missile guidance system, which can be seen in the following video.
For your consideration, the Jericho.
Isn't it mind-blowing how DSP can be used in various fields, right from communication to biomedical applications to military applications? But it is also important to know what it comprises of. And about this, my friend Amemore will talk about. But first, let me call him.
Okay, Fourier transforms. I will do it. I will try to give you an intuition about how the Fourier transform is applied on the voice recording to remove the noise. Look at this photo. This photo contains specks of light called noise. Similarly, the voice recording also contains some background noise. In the real world, professional softwares are used to minimize these kinds of noises. These softwares work using something called as signal processing, which uses a mathematical technique called a Fourier transform. Signal processing is the technique of processing a signal to isolate or obtain the more useful information, such as the recording of voice, and to remove the unwanted information, such as the background noise. And since signal is any waveform that is a function of time, signal processing is not limited to photos and voice recordings. Signal filtering works using a system called an LTI, or a linear time invariant system. Such a system has two simple properties. Firstly, as implied by the name, the system has to be linear. That is, if we put this red wave and this blue wave separately into the system and obtain the corresponding two outputs, then if we input the sum of the red and blue waves, we will get the sum of two corresponding outputs. This is called the superposition principle. Secondly, it has to be time invariant. Suppose if we input this blue wave now and get the corresponding output, then if we input this blue wave 1 hour later, we should still expect to get the same corresponding wave. This symmetry in time is important because it conserves the total energy of the input wave function. Let's see how the LTI system works to filter some background noise. Suppose we have a recording of a voice, but mixed in the recording there is an undesirable low frequency hum in the background. We will take a sound recording and pass it through the LTI system, which in this case can be an audio filtering application. Then in this application, we apply a filtering function such as this one to the recording. if we superpose these two wave functions, we get a new recording that only has the high frequency recording that we want and doesn't have any undesirable low frequency hum. Physically, the LTI system works because of the impulse function, also called the Dirac delta function. When a wave function, or we call it a signal, is passed through a system, we apply the impulse function corresponding to the specific signals that we want. But wait, we said earlier that the recording we have is a function of time. So then, how do we separate the different sound frequencies to isolate the sound that we do not want? The solution comes from a mathematical technique called the Fourier transform. In 1822, Joseph Fourier published his work on heat flow, in which he showed that the functions of a variable can be converted into a series of sinusoidal functions. This was originally used to convert periodic functions to a sum called a Fourier series. Later, it was generalized to non-periodic functions using the Fourier transform. So then, when we apply the Fourier transform to our sound recording, we can decompose one recording into the various frequencies that it was originally composed of. Then it will be easy to isolate the frequencies that are undesirable and apply an audio filter to remove them. Once the filter is applied, the inverse Fourier transform is applied and we get back our sound recording as a function of time.
As Viraj said, digital signal processing has many practical applications. Here we gonna see one of its application, noise cancellation. I have MATLAB program for this. Fs is your sampling frequency, and F is the 10 Hz, which is the frequency of our desired signal. N is the time period which go 0 to 1 with increment of 1 by Fs. X is our desired function, which is a sine 2 pi Fn. And here it is the y. Y is a random function with 1 and length of x. And it is a noise signal, basically noise signal, which we gonna add in our desired signal. Z is the addition of our desired signal and noise signal. NEFT is a number of FFT point, and ZFFT it's a magnitude of Z, and frequency it's a linear vector which contains our magnitude and phase plot. O is the order of our Butterworth filter. Omega n is the cutoff frequency of filter. Here is the command for Butterworth filter, which is a bandpass filter. Here frequency is response of a filter. Z filter filtering our noise signal, and here we gonna filter all of our signal and we gonna plot it. Now I run this function. Here are the plots. So first plot is a sine signal with noise and which has a frequency of 10 Hz. Here we gonna see after applying Fourier transform we get a maximum peak at a frequency 10, and after this we get our original signal. This is the magnitude of our original signal, and this is our original signal.
Of two or more signals and modulation. Digital system processors. So the processes. So what is DSP? DSP stands for digital signal processing, which deals
कट कर ना, तू काय बोलला डायरेक्ट
जा नाही चांगलं केलं तू, चांगलं मला वाटलं नव्हतं रे, चांगलं मी कट करून टाकू याला.
स्टार्ट करू. As Viraj said, digital